So number 65 is a very interesting question. Now, pulling into our knowledge of um, friction and our coefficient of friction here, we know that friction is what provides a force needed for a car to travel around a flat circular racetrack. What is the maximum speed at which the car can safely travel if the radius of the track is 80 meters and the coefficient of friction is 0.40? So here we're given two variables, the radius and the coefficient of friction. Now we want this friction to keep the car on the track, so that's what's going to be our centripetal force in this case. If you remember our fun equation, we know that the force of friction is mu times the normal force. So um, another thing we can know is the value of the normal force, because we know that uh, the normal force has to cancel out with the weight of the car, because the car is not sinking into the track, nor is it floating. So the free body diagram looks something like this, where we have uh, normal force pointing upward that has to equal the weight, or mg, of the car downward, and then of course we're going to have that centripetal acceleration keeping it around the curve. So since normal force equals gravitational force, which equals mg, I'm going to make this mu mg as my friction force. Now we also know centripetal acceleration is equal to mass. I'm sorry, centripetal force is equal to mass times centripetal acceleration, and we know that centripetal acceleration is v squared over r. Since we can set our friction equal to our centripetal force, we know that mu times m times g is going to equal m times v squared over r. And with that limited information they give us, it's still enough, because we know that the masses cancel out, and we end up with mu times g is equal to v squared over r. And we're trying to find that maximum velocity we can attain given that coefficient. So uh, we can plug in 0.40 for mu. We know that g is equal to 9.8, and we're going to have v squared over our radius, which is going to be 80 meters. So we plug that all into our calculator. We should find that v is equal to 17.7 meters per second, or 18 given our sig figs. For number 67, we have a 75 kilogram pilot flying a plane in a loop shown in figure 615. At the top of the loop, when the plane is completely upside down for an instant, the pilot hangs freely in the seat and does not push against the seatbelt. The airspeed indicator reads 120 meters per second. We're trying to find here the radius of the loop. So we know the velocity is 120 meters per second. We know the mass of the pilot is 75 kilograms. In this case, we have to consider our centripetal acceleration. Keeping that pilot in the circle is going to be our force of gravity, or our weight, which is equal to mg. Now the reason we don't consider the normal force, and in this case only the gravity, keeping the pilot in that circle at the top of this path, is because the pilot is in free fall according to the question, and the plane is not pushing against the pilot. So we also know again that centripetal force is equal to mass times centripetal acceleration. So if we set mg equal to m times the centripetal acceleration, conveniently our masses cancel out once again, and we get that g is equal to centripetal acceleration, or v squared over r, based on our formula. So we know that 9.8 is going to equal v squared, so 120 squared over our radius, which we're trying to find. So 9.8 times the radius equals 120 squared, meaning our radius is 1500 meters. And that is our final answer. Right, so problem 74 states early skeptics of the idea of a rotating Earth said the fast spin on Earth would essentially throw people at the equator out into space. The radius of the Earth is about 6.38 times 10 to the third kilometers. So I'm going to convert that into meters. That would be 6.38 times 10 to the sixth meters. So then we want to show this idea is wrong by finding the following. The speed of a 97 kilogram person at the equator, meaning their mass is 97 kilograms. Their speed, again, we're talking about rotational speed here. We can find that by taking the distance that person travels over the time it takes them to travel it. So around the Earth, around the equator, your distance is going to be 2 pi times the radius, in other words, the circumference of Earth, over the time it takes to travel around Earth, which, I'm sorry, the time it takes Earth to travel around, I guess, and that distance would be covered in 24 hours, which is the rotational period of Earth. So if we take 2 times pi times 6.38 times 10 to the 6 meters, we get 4.0 times 10 to the 7th as our distance traveled in a day. And the time in a day, we have 24 hours, but that converts into 8.6 times 10 to the 4th seconds. So then if we divide those two to get our velocity, we should get 463 meters per second. That's the speed that we are rotating around the Earth. Well, not really rotating around the Earth, but rotating with the Earth. So B, we're looking for the force needed to accelerate a person in that circle, which is going to be the centripetal force, or mass times centripetal acceleration, which is going to be m times v squared over r. So we have the mass of 97 times the velocity of 463 squared divided by the radius of 6.38 times 10 to the 6th. So we plug all that into our calculator. We should get 3.26 newtons is the force that it's going to take to accelerate us at that speed. Now that might sound like a really small force, but if you think the Earth has its entire radius to work with to accelerate us, so it's not going to take the Earth much to keep us going in a circle. So now they ask us for the weight of the person. Weight is simply the force of gravity, or mg. So 97 times 9.8 is going to give us 951 newtons for the weight. Now this idea of apparent weight is going to be the weight minus the normal force kind of pushing us away. So that's essentially 951 minus 3, or 948 newtons. Now definitely not much of a difference there, especially with sig figs. We're given it'd be 950 newtons both ways. But essentially, not going to make a difference with that normal force of Earth pushing us off, because Earth's gravitational pull will still overcome us and we won't go flying away just because the Earth is rotating. Now this problem number 80 kind of combines what we were learning last chapter with forces at an angle. We have a 1.45 kilogram ball being swung around with a string with a radius of 0.80 meters. The string is acting in an angle of 14 degrees with the vertical. So what that means is the string is at an angle. I'm going to draw it over here. At an angle holding that ball 14 degrees from the vertical, meaning that if we look at the forces acting on the ball, we obviously have the weight pulling down, but we also have this tension in the rope pulling at this angle of 14 degrees. So there's going to be two components of tension, because if we look at the free body diagram of the ball, we have the weight bearing down, but since the ball is being swung in a horizontal circle, there's no net force in the vertical direction. So that means the vertical direction of our tension is going to be pointing upward. And if we look at this angle over here of 14 degrees, that's also telling us, and I didn't draw it very well, but that's also telling us that this other angle is going to be then 86 degrees. So the upward, I guess, vertical component of tension, if you can see that, is going to be the magnitude of tension times the sine of the angle 86. So then we also have the force that's keeping it in the horizontal circle, which is our centripetal acceleration, and that's going to be equal to the tension times the cosine of 86. Because we're looking at if our tension is downward, we have this horizontal component keeping it in the center. So my centripetal force is going to be my force of tension times cosine of 86, and that's also going to be equal to mass times centripetal acceleration. My weight is going to be equal to the Ft times sine of 86. So I'm running out of time here. I'm going to continue this video in the next part, and then we'll solve for the tension and the speed of the ball.